let's open with a concrete example here. Let's say we're trying to determine the greatest common divisor of 21 and 6. This can be done with a prime factorization or just by inspection here. You notice the greatest common divisor, greatest common factor, is actually 3 here. 3 is a divisor of 6 and 3 is a divisor of 21, and it's the largest number with that property. It can't be 6 because 6 doesn't divide 21. Now you'll sometimes see GCD prepended here. Now I usually leave that out. Some people think it's important to write GCD, but this can't be an ordered pair because it couldn't be equal to an integer. So I think it's context sensitive. But some people like to see the GCD as a prefix here. Now the particular problem we have here is that if you have the GCD of a constant and the modulus to a congruence is greater than 1, it can have at most one prime solution. We're supposed to find out when that can happen. Okay, we're supposed to find out when that can happen. That this type of expression only has at most one prime solution, and you got to find out when that occurs. Okay, it can't, in other words, but it can't have 2, 3, 4, or 5 prime solutions. And by a prime solution, I mean a value of p that you would substitute for n. Now, another way to re-express this congruence, and really it's just an arithmetic sequence, but you can rewrite this as n is equal to a plus some multiple of the modulus, which is b in this case, okay? So we'll put a plus mb, where m is just an integer. M is an integer. So any integer will produce a term that will satisfy this condition right here, if you just remember what the definition of this, it says n minus a is divisible by b, which is equivalent to what we wrote down underneath. Okay? Now, the given is important here. It implies that the greatest common divisor has to be an integer greater than or equal to 2. Okay? And also we can rewrite a and b in terms of d, since d is a common divisor, the greatest one. All right? Now, so again, we just kind of carry on in a straightforward sort of fashion, and we use this equivalency that I talked to you about up here. And when you factor out a d, you see that you get this, what appears to be a composite number, because d is greater than or equal to 2, right? And unless m is equal to 0, this will be a composite number, right? And composite means, but it says at most one prime solution. So that's kind of consistent with what we're looking for. This expression appears to be always composite, but there is a condition, meaning there would be no prime solutions. Okay? Because remember, this is n, and n is satisfies this congruence we're interested in. But the way we've written it here, this is composite, which is an antonym for prime. Okay? Composite means not prime. But I understand that m is a free-ranging variable. M could be equal to 0. So here's something that really kind of gets the problem finished here. N is congruent to 0 mod d. That's the definition. Words. N is a multiple of d. So that means it is 0 mod d. Since any multiple of d is divisible by d, okay, it satisfies the condition of the congruence. Okay? So based on the definition of prime, n is prime if and only if d is the same prime. Otherwise, you would be violating the definition of a prime number. And that probably requires a little more depth, but I'm just going to leave it at that. I'm going to claim that we have proved it, and we would have one prime solution. Okay, and just right underneath it, I'm going to write it a little informally. If the GCD is a prime, okay, and what is it? GCD, did we call it D somewhere? Yeah, right here we call it D. We're going to say it's going to have one prime solution if and only if the greatest common divisor is prime, okay? D is prime. That's what this down here is proven for us, and I'm going to show you some concrete examples. So whenever D is prime, you have precisely one prime solution to this, namely D. Okay, so let's just go down and look at some concrete examples. Right here, I use the same example, 21 and 6. These are going to be elements that satisfy the congruence or the arithmetic sequence. 3 plus 6 is 9, 9 plus 6 is 15, and so on. Notice that every one of these are multiples of 3, and all of these numbers past 3 are composite because they're divisible by 3. Okay? But you see, if you put 3 right here, 3 minus 21 is negative 18, which is divisible by 6, right? But it had to be a prime number. Notice down here, here's something that'll help you make it slightly more clear, I guess. 40, 16, the greatest common divisor is 8. 8 is the largest number that is a factor of 16 and 40. 5 times 8 is 40, and 2 times 8 is 16, so 8 is the greatest common divisor. And so you see 40 would be the first, but you see it's not prime. Okay, it's not prime, and it satisfies this condition. Okay, and you can see that in either direction, all of these are always going to be multiples of 2. All the values that satisfy this would be multiples of 2. Maybe multiples of 8, I suppose. Yeah, multiples of 8, right? Because of the greatest common divisor. 7 times 8 is 56, 9 times 8 is 72, 8 times 11 is 88, and so on. Okay? So hopefully that proves it. I could have been a little more rigorous right here, but hopefully this is clear to everybody that n is prime if and only d is the same prime. Okay? So, meaning, another way of saying that n is prime and n equals d, and they're both prime numbers, the same thing, right? This seems a little more explicit to word it this way, in my opinion, but it can only happen once, even if the modulus is prime. Okay, so this is the so-called answer here. I'll put QED kind of feebly right here. QED, as long as d is prime, you have exactly one prime solution. Okay. D itself. Okay, thanks for viewing.